Hello everybody, welcome to week 9. This is the first of 2 videos for this week. I am going to cut them a little bit shorter because I did hear some feedback about how long the last one was. So let's go ahead and get started. There's a reason that skull and crossbones, Jolly Roger, is there. Okay, our mateys, we'll see how that comes into play later on. So let's get started. Alright, so let's set up this integral and talk about how we would go about evaluating it. It's got a very easy integrand, and here's my domain. Remember, when we're doing double integrals, we're only looking at the floor of that shape, which is an XY plane. So I need the equation for this shape, and that's a semicircle, so I know that x squared plus y squared equals 3. This tells me to do dy first, so I think about how these shapes move in the vertical direction, and the bottom of the shape is always y equals 0, which is nice, and the top is the circle, so I'm going to solve that circle equation for y. Y equals, 9, not 3, 9. 9 minus x squared, and if I square root I get a plus or minus, and I'm looking at the top of the circle, so I'm going to have the positive side. So there's my dy, and now I'll look at my dx. Remember, for dx we look at the extreme points and we want the x values here. This is where x equals -3 and this is where x equals 3. So my x limits are from -3 to 3. So there's my setup, not bad. Let's go ahead and start to evaluate this. So this is easy to evaluate. This is just y. Evaluated from y equals 0 to y equals the square root of 9 minus x squared, dx from -3 to 3. And so this becomes the integral from -3 to 3 of 9 minus x squared, all square rooted, minus 0 dx. And guess what? You don't know how to integrate that. Or you may know, but it's not anything that was covered on how to integrate. In fact, it's not easy to integrate at all. It's possible to do, but it takes about 20 minutes. So I'm going to skip it. We're going to move on. If you want to see it in class, I'm happy to show you, because it does show you some tricks and techniques that are really helpful. And so if you do want to see it done in class, let me know and we'll go ahead and do it. Okay? But instead, what we're going to do is we're going to look at what are called polar coordinates. And to think about polar coordinates, I'm going to go back and think about vectors. Remember when we had a vector in standard position, and this was maybe the point 3, 7. We could find the length of that vector, the distance along here, just by thinking of this as a right triangle. And there's the hypotenuse. And we could find this angle as well, because we know that the tangent of that angle is equal to the y value, this is 7, divided by the x value, which is 3. And so that angle is the arctangent of 7/3. We're going to do the same thing here, except we're going to do this for any point in the plane. If we have an x and a y, we're going to think of it in terms of its distance from the origin and its angle as we measure around in standard position. Okay, so here's an r and here's a theta. We use r's and theta to denote points in this system. So in polar coordinates, if I wanted to plot the point 3 comma pi over 6, I think about going out 3 units and then swinging up so that my angle is pi over 6. And there's the point 3 comma pi over 6. Not very difficult at all, right? All right, let's get another color. If I wanted the point 1, 0, I go out 1 unit and I swing up around 0 degrees. So this becomes the point 1, 0. It's actually the same as in our xy coordinate system there. The point 0 comma pi I already used red, let's use gold. So I swing out 0 from here, and then I go around by pi. There's the point 0 pi. Right there. And let's do one more. Let's look at the point negative 2 pi over 3. Here's how I think about that one. I'm going back 2 units, and then I'm swinging. Think of this as being an arm, and the arm swings up pi over 3. And I go back 2 units. So this is the point. Try this again. Swing it up pi over 3. Got a little number line along here, and I go back 2 units. So this is the point negative 2 comma pi over 3. Okay. So that would actually be the same as positive 2 4 pi over 3, right? Because if I go around 4 pi over 3, here's 3 pi plus 1 more pi, makes it 4 pi over 3, and no, not a pi, a 2. 2 comma 4 pi over 3. So these points have got many, many names. We can give the same point many different names here. All right. Here are a couple of graphs to know about. R equals 3 is actually a very nice graph to know about. In this graph, these are the points that are all 3 units away from the origin, right? That's just a circle. On the other hand, if I have a constant for theta, theta equals 2 pi over 3, those are all the points that are 2 pi over 3 away. So this is theta equals 2 pi over 3, positive and negative. This is where 2 pi over 3 would be. And down here is where negative 2 comma 2 pi over 3 would be. So all the points along there. R equals sine theta. Let's look at this. In the xy axis, this looks like this, of course, and then it repeats and repeats and repeats. And so let's think about this. When my angle is equal to 0, this is 0. Then when my angle gets larger, my radius gets larger until here, where my angle equals pi, this comes back to 0 again. So when these cross the xy axis in the xy plane, they become tangents here. So I have a tangent at 0, and I have a tangent at pi. My radius gets bigger, and then my radius gets smaller. And this makes a little loop. And actually, this is a circle. It has, the radius of this circle is 1/2. And that occurs right here. This is where my angle is pi over 2. So at pi over 2, my r value is 1. There's the center, so this is the center. So the radius of this circle is 1/2 and 1/2. Right there. Okay. R equals sine 5 theta is actually a very interesting one. So for 5 theta, I have 5 there between 0 and 2 pi. This is in the xy axis. I have 5 copies of this loop as we go. And so here's what I'm going to think. This is 2 pi over 5 right here. So at 2 pi over 5, I have a loop. And then I have a little backwards loop. And then I have a little forwards loop. And then I have a little backwards loop. And then I have a little forwards loop. And a backwards loop. and so forth. So I get like a daisy here. These are actually called roses. I get a rose in that case. It's really kind of cool. I think that Desmos will actually graph these, so let's take a look. I'm going to pause for a second and find out. Yeah, as long as I'm using r's and thetas. Here's my little rose. Let's look at the other one. Cosine theta plus 1/2. Hold on a second. R equals cosine theta plus 1/2. Now I'll get rid of this guy. That's called a cardioid right there. So back to the lecture. Okay, why do we care about this? If we set things up in polar coordinates, it might be easier to evaluate. And how are we going to do that? We're going to do it in 3 steps. We're going to change our integrand. We're going to find what our dA is, and then we're going to calculate the limits of integration. So the integrand is not hard to do. Think about when we worked with vectors. Okay, when we had a vector, our r was the square root of x squared plus y squared. So we can think of that, or we can think of x squared plus y squared equals r squared. Another way to think of r is that x equals r cosine theta and y equals r sine theta. So we can use these equations to translate back and forth between x's and y's and r's and thetas right here. Also, we know that the tangent of y over x equals theta. We knew that before. And so we can look at that as well to help find our theta and our r. Our dA is a little bit trickier. So here's the idea. Here's a little delta x, delta y, and when I convert this into polar, it becomes a little thing like this. All right? And here's the idea. When I am closer, my little shapes get smaller. Okay? And when I'm farther away, even though I had the same delta x and the same delta y, my shapes get larger. So I'm thinking about this little shape, and this distance along here is a d theta. No, it's not a d theta. This distance along here is a dr, but this distance along here depends on how far out I am. If I'm close, it's very small, and if I'm far out, it's very large. So this distance is r d theta. If I'm far out, it's large. If I'm close in, it's tiny, and that r puts it in here. So my dA is r dr d theta, and that's where the pirates come in. In polar coordinates, you got to think of pirates. Your dA is not just dr d theta, it's r dr d theta. Mateys, I know that's a corny joke, but I hope it helps you remember this because it's really important. You'll get wrong answers otherwise. And your limits of integration you get from looking at the picture. So let's come back and look at an example. Okay? Here's our first example that we started to work. 1 dy dx. So I'm going to change my integrand. There's nothing to change. Okay? I'm going to change my dy dx into r dr d theta. And now I'm going to get my limits of integration. I have r on the inside, so r is always from the center, from the origin out to the shape, and the shape is a circle, so my r always goes from 0 to 3. Okay, now I'll look at my d theta. I think about where theta starts. Here's where theta starts in this shape, which is 0. And theta goes all the way around until I hit over here, and that is theta equals pi. And now, this is easy to calculate. This becomes 1/2 r squared from r equals 0 to r equals 3. And I'm still integrating from 0 to pi d theta. And this becomes 1/2 times 9 minus 1/2 times 0 from 0 to pi d theta. And this becomes 9/2 theta from 0 to pi. And this becomes 9 pi over 2. And we can check this in this case because I'm only integrating, my integrand is just 1, so my answer should come out to be just the area of this semicircle. It should. Well, the whole semicircle is going to be pi r squared, which is going to be pi times 3 squared, which is 9 pi. We have half the semicircle, so bingo. Easy, easy peasy to do. There's my check. All right, because we're moving into things where you have some trigonometry, there's some trig facts, some identities that you need to know. You need to know your basic trigonometric identities. Your basic ones are things like secant of x equals 1 over cosine of x. Whoops, x. Tangent of x equals sine of x over cosine x, and so forth. Those are your basic ones. You also need your Pythagorean identities, and there are 3 of them. I only remember the first one. Let me change to thetas instead of x's. Sine squared theta plus cosine squared theta equals 1. And then I think, oh, if I divide the whole thing by sine squared theta, that gives me 1 plus cosine over sine is cotangent, so cotangent squared theta equals 1 over sine squared theta is cosecant. And then if I divided the whole thing by cosine squared theta, that gives me tangent squared theta plus cosine over cosine is 1. And on the other side, 1 over cosine is secant squared theta. So there are your 3 Pythagorean identities. You also need maybe, yes, you do. I'm not sure if it comes up in this homework, but I have seen it in the homeworks in this class. The double angle identities. Here's how to remember those. Is to remember cosine of 2 theta. That's cosine squared theta minus sine squared theta. You got to know that one. If you know that one, you can also use it to find a lot of other identities. For example, if I turn that sine squared theta into a cosine squared theta, this will give me cosine of 2 theta equals cosine squared theta minus 1 minus cosine squared theta. So I'm using a Pythagorean identity to turn that into a cosine. And that becomes 2 cosine squared theta minus 1. And then if I take these, I can find that cosine 2 theta plus 1 all over 2 equals cosine squared theta. You can do the same thing for sine. Just go up to the very first one and change that cosine squared into a sine squared, and you can solve for sine squared theta. Here's why this is so important. You can't integrate cosine squared theta d theta. But if you use these double angle identities, you can definitely integrate it by using that identity. Let's see. Also, sine of 2 theta is 2 sine theta cosine theta. That one gets used not as much, but it does get used a little bit. So you should know those identities. You should know all the basics. You should know all 3 Pythagoreans, or know one and know how to get the other 2. And these, you should know how to find them. Okay, so if you can remember the cosine of 2 theta, you can get the other ones easily. You should also know how to solve right triangles. So for example, if you needed to find the sine of the arctangent of x over 3. You should know what to do with that. And here's the idea. I'm going to set up a triangle for a arctangent of x over 3. Here's a theta, and the tangent of theta should be x over 3. So that angle is the arctangent of x over 3. Now, if I need to find the sine, I can finish the triangle because I know the Pythagorean identity. 9 squared plus x squared. Whoops, not 9 squared, 9 plus x squared square rooted. And if I need the sine, now I just pick it off of the triangle. X over the square root of 9 plus x squared. So you should know those as well. Okay, so those are the things from your history, from your pre-calculus history, that you're going to need to know. All right, moving on. Triple integrals is going to be in the next video. So see you later. Bye-bye.